Hi, this video is going to discuss conservation of momentum. And as with the other stuff we've done, we have here an example problem, but I really do want you to pay attention to kind of the big ideas and see if we could set this up so that you could explain it in other situations. Conservation of momentum we can find all around us. In fact, it is one of the most fundamental things in the universe. We have not been able to find any examples where if we properly account for everything, that conservation of momentum does not hold true. And this actually leads to some very interesting and weird stuff in modern physics. Okay, but more back to our basic mechanics. We have here a situation of two objects crashing together. We have two train cars that are moving toward each other. And honestly, anytime we have this kind of thing, things collide, it can get kind of messy, but conservation of momentum helps us skip past a lot of the messiness. We don't know what the force was at all the different times, or we don't know all the details of what was happening during the collision. But conservation of momentum lets us figure out what the change was and worry about these individual objects by looking at first what we know about the whole. And here's what we know for the whole. That the total mass times the velocity of the center of mass will equal the mass of the first object times its velocity plus the mass of the second object times its velocity. Now, this equation will look a lot, in fact, exactly like how we calculated the center of mass. Well, all we've done is replaced position with velocity. And this is true. Now, here's what's new. If there are no outside forces, if this is a closed system, if nothing else from outside is pushing or pulling these cars, then the velocity of the center of mass will not change. And so I could have, for two different objects, what we have is the momentum for one object and the momentum for the second object. The total of these two cannot change if this isn't going to change. So for example, in the beginning, before they crash together, we have mass of object 1 times velocity of object 1 original plus mass of object 2 plus times velocity original of object 2. That's doing this calculation for before the collision. But we can also do it for after the collision. Mass of object 1 times v final for 1 plus mass of 2 and v final for 2. This is also equal to the total mass times the velocity of center of mass. And we know this can't have changed if there have been no outside forces. So if these cars are only exerting forces on each other and not experiencing forces from outside, then these things have to be true. Okay, so we take this idea that the total momentum before and the total momentum after will not change, and we can rewrite it in a more specialized form. What we can do is we can look at this and say, hey, these two objects, they start out separately. So before the collision, here's my total momentum. After the collision, they start out together. In fact, they have something that looks a lot like mass total, so m1 plus m2, times a single final velocity. Now, you might be going, how does that match what we have down here? Well, if they're stuck together, v final 1 and v final 2, they're going to be the same. It's just one object, one velocity. And so what happened here was when they got stuck together, they became one object, and the velocity of the center mass is the velocity of that object. Okay, so let's actually use that in the problem solving here. Let's look at our givens. So, mass of object 1 is 150,000 kilograms. And we know that it's moving at 0.3 meters per second. Now, we don't know which one is right and which one is left, but we know they're moving toward each other. So let's say this car, object 1, is moving to the right. Now, mass of object 2 is 110,000 kilograms, and we know that it starts out moving in the opposite direction. So object 2 is moving at 0.12 meters per second, but it'd be to the left. And we always have to be on the lookout for things with opposite directions, because when we have opposite directions, that means we're going to need a negative in there. So, okay, I hope it makes sense to you that if I come over here and draw, train car 2, and it's moving this way, that he's going to have a negative velocity. Now, they're going to end up stuck together, but we do have a question. Which one of these wins? When they're stuck together, joined effectively as one object, which way are they going to go? Are they going to be left or right? Well, we can do that. We can figure that out as we solve for V final. And as we mentioned, if we take the equation for what's going on here, momentum of object 1 plus momentum of object 2 beforehand equals the momentum of object 1 and 2 together after, and solve to get V final alone, I get that V final should be M1 V original 1 plus M2 V original 2, and divide it by the total mass of these two put together. And just like in some of the previous problems, this is where working in positives and negatives can get to be important. Now I'm going to erase this and to show the substitution. So take a look and make sure that you understand what's going on right here. Okay, and then if we actually solve for that, our V final for the two of them put together, mass 1, 150,000, times velocity 1, 0.3 meters per second, plus mass 2, 110,000, times V original 2, we had a negative 0.12. When these two crash together, their momenta are canceling each other out. The momentum for the two objects is in opposite direction and works to cancel out. Okay, and we divide that by the total mass of 150,000 plus 110,000. So, we do some calculations, put it in the calculator, once again making sure that we do all the calculations for the top part and don't mess up our order of operations and paying close attention to negatives and all that good stuff. I get positive 0.122 meters per second. In other words, the two of them are going to move. We said our 0.3 meters per second was positive, and so it's moving in the direction that car was. In the way that I drew it on the previous screen, that was to the right. And so we can get the V final of this object. Now, understand that we could have solved for any one of these unknowns, any one of the variables that we have in this equation. And there are several forms of this equation, but these are just groupings. So it all goes back to remembering, what is the total mass and the velocity of center of mass, and we figure that out by taking the momentum of the two or more separate objects, and we just figure this out before and after the collision. So in this case, we had two separate objects before the collision. We had one big object after the collision. But in both cases, it's the momentum of all the objects in the system. All right, good luck, and we'll see you next time.